presentation. Okay, let's hope that everything works with the audio. So it's my pleasure to announce our next speaker, Thomas Roland, and he's going to present us his work about pronunciation software tool with gamification elements as well for children, please.
Hello. I'm just checking that. Yeah, it is easy to. So yeah, I'm going to present the work I did in the context of my thesis in the TAPAS project. And this work has been done in Escaide in Portugal and under the supervision of Alberto Abad. So first, I will just start with a bit of introduction. So for children, like speech communication disorder can lead to different problems. It can be feeding and swallowing, articulation, fluency, voice. And all of these problems are quite important because, as you know, like when you're children, you need to express your feeling, you need to express your need. And when you're not able to communicate and to express these needs and this feeling, then it's not good for the development of the children. And therefore, when children have this kind of disorder, usually like most of the time, we send them to speech therapy. That's usually take place in an hospital or a clinic, but also because you need to exercise a lot. Well, most of the time therapists like send exercise, also ask the children to do exercise at home. And there is some drawback in a way to this current setup. So first, you need an expert therapist, speech therapist, and this is not easy because it's a very complex topic. Also, you have the problem of the limited attention span of children. Well, ask to a children to do a boring task in a way, like for more than half an hour, like you will just want to look outside and do something else. And also the fact that hospital and clinics can be stressful environment for children. Going to hospital can be stressful. So these three drawbacks can be kind of tackled by speech and language technology tools. So for instance, the need of experts can be replaced by a specialized algorithm or artificial intelligence. For instance, if the children is at home, usually it's the parents does the parent do the assessment, which is not as good as a clinician. So this specialized algorithm and artificial intelligence algorithm can provide probably more like insightful feedback to the children. For the limited attention, we have the gamification. So we try to, with this gamification framework, to really keep the interest of the children like interested in the exercise. And finally, of course, these SLT tools allow to work at home, and it's way less stressful than environment. So at Escaide, so in Portugal, where I'm working, we already developed some SLT tools for children. So I show some of the examples, some example of SLT tools. So as you can see, it's very like colorful and very like children kind of games. But yeah, for us, for this presentation, what is more important is what is like behind these tools. So we can most of the time like synthesize these systems as follows. So we have the children patient, and the therapist, and we have here our system. You can see the mouse. So there is an exercise which is created, so it can be like repeat this sentence, repeat these words, and it is presented in a gamification framework to the children. So with like this kind of like presentation. And then the children will like speak. It's gonna be like sent to a speech recognition system that's sometimes has a priori knowledge about the exercise. For instance, if we ask the children to read a word, we already know what the word, the expected word is. So we have this a priori knowledge. And then after this speech recognition, like we have like the results, and we can like detect the mistake recognition. Usually what we do to assess the pronunciation, we use posterior, because what we have at the output of the speech recognition is posterior probabilities of characters or phonemes, and then like we just look at the posterior probabilities. and it gives us like the mistake, like the mistake recognition. And then depending on the mistake, the exercise is updated. So if the children have some issues saying a type of words, then we're probably gonna like propose this kind of word like much more often. And statistics are given back to the therapist that can also update the exercise depending on the needs. And we can also, so the statistics here are mostly like mistakes and mistakes when on the reading task, but we can also like add more things, and that's what I've been doing also in my thesis, such as pathology and disease information. And I'm gonna like spend a bit of time explaining how it works, because it is quite interesting to see this statistics. So, and during this presentation, I'm gonna mostly focus on presenting these two components. So let's go directly into it. So pathology and disease information using speaker embeddings. So first, what you need to know is like when you speak, you have, of course, the linguistic information, which is the text, but you have plenty of other information, which is paralinguistic. It can be the speaker ID, the emotion, the age, the gender, etc. But also, and that's quite recent, pathology. So the speaker embeddings, what is it? We have, for instance, here two speaker. We have, so this first speaker is gonna say two sentences, well, two utterances, one green and one yellow. And the second speaker is gonna say the blue one. So we have this speaker embedding instructors that I'm not gonna go too much into details because I don't have time today to present it, but it's mostly the I vector is more statistical based and the X vector is more deep learning based. And this black box, these speaker embedding extractors, well, what they do is like they take this audio utterance and they convert it into a single vector. And hopefully, if it's work well, like if you have the same speaker, the vector should be closed. So here we can see that the green and the yellow are closed. And if the speaker is different, like it should be quite far from the other one. And then so the method we use is we take these vectors. So we have all of these vectors that we extracted with the X vector and I vector extractor. And we use just a classifier. In our case, we use SVM, and we try to detect a pathology or not. So I'm going to show just a few examples. I'm going to go very quickly because I don't have much time to go into details. But for instance, we did that with Parkinson's disease and obstructive sleep apnea. So we have here some patients, some control, and same for the obstructive sleep apnea patients and control. So that's just the data set we used. And what we can see is if we compare with knowledge-based I vector and X vector. So knowledge-based is just, like knowledge-based, like features. And the I vectors and X vectors is just the different extraction. And then if we do segment, and here it's just speaker. So segment is just the current utterance, and speaker is like a majority voting. And what we can see is that using these embeddings for Parkinson's disease, we can detect quite nicely the disease. And we can see like quite the same behavior in the obstructive sleep apnea corpus. So just to say that it worked. So we can give with speaker embedding, we can at least like understand these two, detect these two pathologies. And then we did the same with during the anti-speech address challenge. So which is Alzheimer's disease corpus. So here I also plot some statistic information about the data set. So control and Alzheimer's disease. And what we can see is it also works. So we have also like something that's the I vectors and X vector extractor. Like they give this speaker embedding gives nice results. So that's nice. The speaker embeddings can give like information about pathology. And we also try with different things. We tried also with COVID-19, but yeah, I'm not gonna go much more into details. So yeah, so that's nice. We have this pathology and disease information, but the very focus of my thesis is more the automatic speech recognition model, because to understand if what the children say and to like get nice posterior probabilities and then detect correctly the errors, you need to have a good ASR model in the first end that work well for healthier children. So the most focus of my thesis was to address this problem of yeah, having a good model, ISR model for children. So why? Because if you use an ISR model for adults, it works well, especially with deep learning. But then if you use it with children, then there is a huge drop of performances. And this can be explained by mostly like three main factors. The first is the eye, enter, and intra-speaker acoustic variabilities. And this is explained by the fact that the vocal speech production system is growing over time. Then the second reason that's the drop of performances is a limited linguistic knowledge of the children. And of course, since we are in this deep learning area, and times data is more important, and we don't have that much data for children. So these three reasons are why we have a drop of performance in children automatic speech recognition compared to adults. And the contribution of my thesis was mostly like in three main parts. So the multitask transfer learning approach that I'm not going to talk today, the adaptive transfer I'm going to talk today, and we also did like a benchmark with self-supervised learning. I'm not going to talk also about that today. I'm just going to talk about the adapters because it is like the most like nice thing to talk about, I think. So, okay, let's dive into these adapters. So what is adapters? First, where do we use these adapters? So when we use automatic speech recognition system, nowadays we use end-to-end model, which means we directly take the audio input or the FBanks or like acoustic information vectors, and we directly like output the text. We don't have, as we had in the past, an hybrid like HMM, GMM, or HMM, DNN. Here's like directly like end-to-end. And the best system for end-to-end children automatic speech recognition nowadays is transformer-based, which relies mostly like only on attention mechanisms. And the problem is if you, well, as I mentioned, like children are growing over time. So if you want to have a system that works well for young children, then it's probably not going to work that much on older children. So you have this problem that you need to train like almost like group-based system. And this transformer model are like super big, so that we have a storage cost, but also they are long to train, so we have also a training cost. And when we do fine tuning over the system, we also forget the previous models because like we fine tune all the weight. So this is quite a problem. And for that, we propose to use adapters. So that's something that have been used mostly in LLP and quite recently on automatic speech recognition too. So how it works is if you take this is like a transformer layers here, also here in the decoder, you take this and you just add like here, like this block, which is the adapter. And when you're gonna fine tune, we're gonna froze all the weight of the transformer. You're just gonna train the adapters. So, and the adapters usually is just a norm fully connected down and fully connected up. And what we proposed is to have also a variational adapter. So our motivation is, as I mentioned, children has a lot of variabilities. So what if we just like capture these variabilities here with like kind of variational encoder kind of in the adapter? So mostly the idea is like we're gonna capture like the mean and the variance, and then we're gonna like depending on this mean and variance, we're gonna like create a new sample Z conditioned by these two, and then we're just gonna decode. And at inference time, we just get rid of the variance, so we only have the mean. And during training, you learn what is the mean and what is the variance. Well, I think I'm gonna skip that. Okay, so that's the children corpus we used. So quite a big one, which is a My Science Tutor children speech corpus. This is just like the experimental setup. So just the model we use, it's not really important here. Yeah, here it's more important. So as I mentioned, there is a drop of performance. If you don't fine tune an adult model, you already have this score. And if you fine tune it, you have like this score. And as you can see, there is like already a huge drop of performances, which means that the system has to see some children data. But the problem is, if you look at the number of parameters that have been trained during training, it's quite a lot. And it means that if you want to save this model and use it, you also need to store that. And with the adapters, so the simple adapters, we already reduced like a lot the number of parameters, but then we are very close in terms of scores. We are like just 1 point behind, but we use like almost like 16 times less. And then we just assess like if we do these adapters in the encoder of the ICER and the decoder only. And what we see is, yeah, it's better to have it in the encoder only. And then we have our variational adapter. So as I mentioned, is like with these 2 branch instead of the 1, but at inference time, we get rid of this variance here. And we don't, which kind of look like the normal adapter, but just at inference time. So this is here the result of our variational adapters. Even so, the number of parameters trained are higher here. In inference time, they are exactly the same as the one here. And what we can see is we get even closer to the fine-tune score with way less, almost like 10 times less, like with almost more than 10 times less parameters. So it worked well, and we did the same experiment with encoder and decoder. And yeah, I think I'm good in terms of time. And that's the current work and the future work. So what we're doing right now is we're trying new adapter architecture, like using these speaker embeddings. And we also, since we can train different adapters for different children group, we also want to like merge them together using attention. So that's called attention fusion of adapters. And we also want to use TTS as the documentation. As I mentioned, we don't have a lot of data for children. So, well, it's a PDF. I can't really play the sound, but we have a system that creates children data set depending on the speaker embedding. So we can create as many children data that we want. And right now we're trying to make it work correctly because we still have a bit of artifact in the TTS, but yeah, that's mostly it. So yeah, thank you for your attention. That reference, yeah, that's of the talk. And I have like more scores, but yeah, let's not go into that. Yep, thank you.
Thank you, Thomas, for talking us quickly through all your work that you did. I think it's very interesting. So looking to the audience here first, are there any questions? Yes. Great.
Thank you very much for the very interesting, very good presentation. So just about this adapter. So one of the goals of using this adapter architecture is that you avoid this kind of a catastrophic forgetting that happens. Can you somehow, did you try it? Did it actually work? Did you get rid of that problem somehow? Can you somehow demonstrate that it actually remembers something?
Yeah, so as I mentioned, the adapters, we just add these adapter layers in the transformer and we froze everything. So the way we get rid of the catastrophic forgetting is just we remove this adapter and it's exactly if that there wasn't an adapter. So there is no catastrophic forgetting at all.
When you have a child talking, then you just switch on the adapter, but otherwise you would use. Okay, thanks.
Yeah, and the idea is we can even like have like groups of adapter. Like if we have like younger children, we can train an adapter on younger children, and you can like plug the right adapter instead of just like loading the entire model. So that's yeah.
So if I can you comment about training times, like fine tuning versus training an adapter?
So adapter are faster to train because of course you have less layers and less weight to train. So yeah, it's much faster. I can give an example. For instance, right now I'm using adapters and I can train a system like like in 1 day, while I think the full training will be like at least a week. So it's much faster.
The online question.
Online. But in between, Thomas, it's language dependent, the adapter, but you can train it fast for another language. Yes. Okay, thank you. Okay. Okay. Yes. The people online can ask their questions too. Diana, you have a question?
Yeah. Thank you. Thank you very much for the talk. Very interesting. I'm also interested in the future work you are pointing out about data augmentation using synthesizing directly children's speech. I guess you have some antecedent, some previous work that makes you feel that this is going to work. Can you talk a bit about it, or you have seen some already TTS that you have tested and could provide some useful speech for this?
Yeah, so for the TTS, there is some recent work. So I think it's from ICASP last year, where someone tried to use TTS as data augmentation. It's work better than mine. I think it's because they have less children. Like mostly what they have is they have a limited amount of children. And in my case, I don't have a limited amount of children. I can create a speaker embedding on the fly. So I can create as many children data that I want. But yeah, there is like some previous work that show that TTS for children is working. And also for adults, even so, yeah. Does it answer your question?
Yeah, the one thing, can you point out some in the chat? And also if you have seen some of the same idea, but for pathological speech. I mean, children that are speaking, yes, with dysarthric or well, something less than dysarthric maybe, but some pathological speech.
With the TTS, creating like
Yes.
TTS. Yeah, of course. It's something that's need to be tried. I don't think I see that many works on that. But I guess you just like the way you should go is like you have this TTS system working well for adults, and then you just fine tune it with the pathological speech. That's something I can also try. I didn't try it yet because my main focus is the children, but yeah, that can be something I can try. But yeah, I don't know if it answer. I don't know if it answer your question.
Well, what I'm interested in if there is some TTS that actually works okay for pathological speech. In my case, for adults, but as I saw that you are planning to test it on children,
yeah,
like, for the reason I'm asking.
I think if you want to training for pathological speech, you have like we have the same problem with children. Is if you just generate like the TTS utterance out of it, you can have like some very distorted and like some that's very badly generated one. So what you need to do is what I'm doing with the children TTS system is when you generate, you have to select the data that you're gonna keep in your data set, TTS data set, because the one that are like really distorted because the input is distorted like also. So you need some data selection process. So usually what people do is they take the X vector of the original speaker and the X vector of the TTS, and they just do like a cosine similarity, and depending on how well the cosine similarity is, they keep or they don't keep the utterance in the data set, the TTS data set. Well, it's just data selection. You need to select the data you're gonna keep. You can't just generate.
You mean that fit the? Yeah, you mean that fit the TTS with, for instance, a pathological speech data set. I was testing this with indeed with a data set in Portuguese with pathological speech and was not. I don't know. I didn't find a very well approach at the end.
Yeah, for pathological speech, I don't really know because I'm mostly focused on children, but I guess the issue is more or less the same as children. So yeah, data selection is quite important there.
Okay, and about data augmentation, the usual, I mean, not TTS, just doing some normal data augmentation, just changing the speech. I mean.
Yeah, there is a lot of work on data augmentation for children and even like for pathological speech. Some people use GAN to transform adults to children's speech or the opposite way. Yeah, so there is a lot of works some people also use adversarial networks to not really GAN, but more adversarial networks to try to close the gap between healthy and not healthy, at least in the recognition. But there is a lot of data augmentation techniques there.
Okay, thank you for the comment.
Thank you, Thomas. Thank you, Diana, for all your questions. And I think it's time to move to the next presentation. So give me a moment.